All right, welcome back. So today, now that we have motion planning safely under our belt, I get to talk about mobile manipulation. Okay, so the whole semester so far, we've only exclusively done robots bolted to a table or, well, floating in space, and there were bins put next to them. Okay, and in fact, a lot of my research, I would say, has been with robots strapped to table. I did walking robots before, but my work in manipulation has been mostly with robots strapped to the table. And I think that's, like I said, it reflects my biases a little bit because I like the dexterous things with their hands more than I worry about the navigation and other components. But I think it limits, I don't want it to limit your thinking or my thinking, right? So a lot more interesting things can happen when you go mobile. And I want to sort of talk through some of those the assumptions that we've been making so far that kind of break, or at least the emphasis that has to shift when you start getting out, instead of bringing interesting objects to your robot, the robot's going to run around and find its own problems. So there's a new cast of characters now. So meet a few of the famous mobile robots out there. Maybe the most famous of all is this PR2 robot by Willow Garage. It was a fantastically successful project. Willow Garage was a sort of a venture-backed research farm that made this robot, with Ken Salisbury being one of the lead designers. And they delivered these to a handful of academic labs and funded them for a handful of years. And it sort of started at the same time as Ross, and it really started this ecosystem of people sharing code around robots. And it was just a good robot. Leslie and Tomas still talk all the time about how much they missed their PR2, which slowly broke down and wasn't supported anymore. For a while, they were buying every spare part on eBay to try to keep it alive. I met somebody just at iRoast not too long ago that said that they managed to keep theirs alive. They've been putting new parts in and everything like this. So it's kind of a Frankenstein PR2 now. But people love this robot. Eve, it used to be Haloti robots. Now it's been renamed to 1X. Is a, sort of a humanoid form factor with a wheeled base. It's a beautiful robot. I showed you the Toyota Research Institute mobile manipulator. This is the version that's picking groceries. We've had versions that are working in the home before too. There's also been a series of sort of one-armed robots. Those were all bimanual, and they were sort of somewhat human-formed, right? You might have seen the Fetch robot running around. Fetch has now been acquired and is more focused on the base, and they're not building the upper body, to my knowledge, anymore, but this was a common robot you could see around often. Toyota had a one-armed human support robot. Everyday robot from Google, the project sort of famously got shut down, but the robots continue, and they've been adopted by the Google DeepMind group and Google Brain, Google DeepMind, and they're a sort of a one-armed mobile robot. And of course, we've got some legged robots too. I didn't list them all here, but Spot by Boston Dynamics is now a mobile robot, by virtue of having an arm strapped to its top, right? And this is fantastic. Now, the one thing I want to say, though, even though there's an array of these robots out there, and I can show a lot of cool things on the picture, it's actually, if you want to work on fixed base robots, there's a handful of robots that you would consider buying, and it's easy to get one delivered. If you wanted to do research on a mobile robot, it's actually harder to find one that everybody loves and that you would just naturally buy and start to. So even though the pictures tell a slightly different story, I think there's actually a shortage of mobile robot offerings, mobile manipulators out there. Maybe the market isn't quite there yet. I think as soon as there's like enough researchers that want them, maybe that could get it off the ground, and then a product that's around the corner, then maybe we'll see something different. But right now, it's kind of a starving market. Yeah? Yeah, so some of these have been pretty successful, but let's say a lot of them have. I don't want to maybe diss on anybody's robot, but there's things that maybe don't fit the bill. Some of them are just reliability, maintenance, cost. But but it's actually pretty hard to find one that you could build a research program around. There's a few out there, and there's more and more coming out all the time, so we're hoping for the best. Okay, but so something interesting happens once you can start moving around, and some of the problems, like I said, that some of the assumptions we've made you have to break down a little bit. So the goal for today is just to kind of tell you a little bit and pick a few places to dive a little deeper about what happens, what's different when you start going mobile. Okay, so I'll say a little bit about what's different about perception, and this is perception as we've been talking about it so far, and forecasting some of the other perception work we'll do, but there's some things that just fundamentally change once you're mobile, which I'll make these points in more detail, but just to give you sort of the outline. One of the things that changes is sort of you have to deal more often with partial views. We put a lot of cameras around our scenarios before. You don't get to do that anymore. You've got head-mounted cameras, maybe robot-mounted cameras, but that's it. We made a lot of assumptions before about our environment. Those tend to break down when you can run into any possible house or something like this, right? And most importantly, maybe you have to somehow estimate your state. So this, you guys maybe know my notation now. So I see for camera, you don't know where the camera is in the world, except if you try to spend time doing state estimation. And that, we'll see how that entered some of our assumptions already. What does it break about or change about kinematics and motion planning, right? So we have a mobile base now, which you have to think about the right way to handle that. And the answer is different if it's a holonomic base versus a non-holonomic base. And there's some other details that pop in, like if you can spin 360 around, then you got to sort of deal with that carefully. Otherwise, you might do the wrong thing. And I might have a sad story about us doing the wrong thing and losing $2 million. Okay, but that'll be at the end. But in general, actually, the kinematics of our robot, I think if there's one thing you take away here, the kinematics of your robot is actually typically way better once you've got a mobile base. Okay, so a lot of the kinematics problems that I've dealt with in recent times of trying to like reach a big arm into a little sink or reaching into a cupboard or something like this, they actually get a lot better if you can just move your base. Your kinematic workspace improves dramatically. Tomas always says, like, you're just solving a problem you don't need to solve. If you just move the base, everything gets better. What's different about simulation? So I think the demands on these sort of problems get bigger. You end up doing larger scale scenes, thinking about how do you build procedural worlds, okay, as opposed to just a couple spam cans. And I won't talk much about navigation, but there are new problems that come up. If you just have to decide where to drive, build maps, understand how to move through the world, then there's new challenges that come up in mobile manipulation. Just figuring out, just being mobile, period. Okay, so let's dive in. So I'll say a couple of those things in a little bit more detail here. So I showed this figure before, right? When we were doing the dish loading task before, we put a lot of cameras up. Why not, right? If you've got a fixed environment, you can afford to measure your cameras. You know that ICP and other methods are going to struggle with partial views. It makes sense to put to instrument the environment with as many cameras as possible. We did that a little bit with the bins, right? In the bin clearing example, I put 3 cameras around each of those bins. And that does help, right? That really, you can see the mustard bottle from multiple sides. That's the difference between being able to pick an antipodal grasp or not being able to pick an antipodal grasp. If you have a camera looking only at one side, right, then you're only going to get the front half of the mustard, and there's no antipodal grasp available, right? Unless you do something about shape completion. Okay, so trying to guess what's behind there, or you can actively perceive and move around the world and try to sort of collect more points. But you're fundamentally now limited to, you're still in a situation where you might have lots of sensors. It doesn't really hurt to put more sensors on. We want rich point clouds, we want redundancy, okay, but they all tend to be coming from the same direction. I think I told you when I brought in some of the hands from Atlas, sometimes you get cameras in your hands, or wrist-mounted cameras are pretty common, and that can allow you to give, get good views when you get close to some extent until you get too close, and allows you to see from other views. But still, you're very much a human-centric, robot-centric view of the world now. And that does change things. So I think the answer, and I won't speak too much about partial views now, because the real answer for partial views, I think, is learning. Right? This is actually a place where I think the fundamentally correct answer is to use machine learning to do this. Geometry alone doesn't give you the answer. What gives you the answer is the statistics of the world. Right? The reason that you can guess what the back of the mustard bottle looks like is because you've seen some distribution of shapes in the world, and the mustard bottles, you've seen mustard bottles, and so you can infer from more than the current sensor inputs. Right? Geometry can do a lot with the current sensor inputs, but at some point you need to infer beyond that. You need to have priors, and that comes from data, basically. That comes from statistics, let's say, for sure, and probably from data. Okay, so I think the fundamental way to get around partial views is just by learning. All right, let's think about the fact that we're going to be moving through lots more environments, right? So I grabbed this from one of your P-set problems. You remember that? Just trying to do ICP on the red brick in the bin. One of the steps there was subtract away the background, right? And we've been doing that a lot, sort of in the details there is you kind of assumed that you knew where the table was. You assumed you knew where the bin was. You could crop that out of the point cloud and be done. If you don't know exactly where the table is, or if you don't know, it's enough to not know, right? So basically, that assumed a few things, right? It assumed that we knew where the table was in the world, right? And that was fixed. And then implicitly, it assumed that we knew where the camera was in the world so that we could understand where the table was relative to the camera and subtract it out, right? If we had both of those, then we're good. So I think once you're a mobile robot and you're going into everybody's home, for instance, then I didn't mean that to sound creepy, but that's for service, to be nice, right? Then suddenly you might not know the table. You might not know the exact model of the table that they're going to be operating on. You need a more general concept of table. But also you have just an estimate of the camera, okay? So you're going to have to infer the geometry. You're going to have to segment out the objects that are needed from the objects that are static, okay? And that really does sort of change the game in what you have to do in mobile manipulation. I think John Leonard, he always teases me because, he gives me a hard time with our fixed-base robots. He's like, when are you going to go ahead and solve the full problem and actually do some state estimation? Okay. So estimating the state of the robot, more generally, this is somehow the state of the robot in the world, and so you can understand the state of the camera, requires state estimation. And that's a big field in and of itself. And you can take an entire class on probabilistic robotics. What happened to probabilistic robotics? Okay. But it really starts to matter once the kinematics between your camera and your objects are not fixed. Okay. One of the things that, maybe just to say sort of from a practitioner's view of that, since I won't do the whole semester's worth of material on that right now, but you have a handful of sensors in which to do the state estimation when you're a mobile robot. You typically have an inertial measurement unit, right? Inertial measurement unit. You typically have wheels odometry. Right, the amount of rotations of your wheels, and if you assume that they don't slip, they should tell you to some extent where you are, and it tells you measures accelerations instantaneously, okay, and where gravity is, okay. But these are hard to do by themselves. I think the cameras have turned out to be the most powerful of the sensors, right? So, or depth cameras. And these days, people You might have heard of simultaneous localization and mapping. SLAM is sort of the big name for it. But even working directly from cameras, people do a lot of visual inertial odometry. To try to use just even RGB sensors to try to estimate relative displacements and estimate the state of the robot as it's moving through the world. Okay? But that all becomes relevant once you're not fixed to the table. Yeah? Yep.
So is that the camera on the robot?
That's the camera on the robot. So I want to pick some frame on the robot. Maybe I could say inherently I've got the robot base, let's say. And this is the one that's hard to estimate, right? And then the robot base to the camera is, I think, back in the place where we're relatively known, right? It still requires using robot sensors to do it, but the quality of the measurement in our encoders on each joints tends to be, we'll see examples in dexterous hands maybe where that breaks down, but in general, I have a pretty good estimate of where my relative pieces of my robot are, and the hard one is knowing where my robot is in the world. Thank you for asking. Okay, so if we don't want to know we don't want to, I mean, you could say I'm going to have a library of models, and people have used to think more this way, honestly. We're going to have a library of models, and we're going to do ICP, for instance, to register all of the things in the world to some model or to some discard pile, let's say. Okay, and so the way I'm going to manipulate the things on the table is I'm going to find some canonical model of the table. Or at very least, I could fit a plane to it and start trying to model the pieces of the world. And that gets you somewhere. But I think you also, once you're into these more novel environments, the same way we developed some tools that were less dependent on known models for manipulation, right? First we did ICP, and then we did antipodal grasps. Antipodal grasps didn't require detailed model knowledge, but they were able to work for a lot of different models. Okay? The sort of comparable assume less about models for the environment as opposed to the objects has some other relevant ideas about sort of how do you generalize, how do you just treat the complication of the environment without having to model everything perfectly. Okay. So if you think about the requirements for something like that, there's a bunch of different choices we could make for modeling the non-manipulation part of the environment. But probably we want something that's going to be well connected to sensor data. We want to have it support motion planning queries, okay? In particular, we want to have things like fast collision detection. And support for things like min distance constraints, if we want to use trajectory optimization. Right, this would support sampling-based planning. This would support trajectory optimization. So if you've got a bunch of point clouds coming in, and you don't need to manipulate everything, then how should you represent those point clouds in order to sort of support these kind of, I want to not run into things, but I also want to not have to model everything. Yeah.
Are we thinking about like supporting multiple stories, which are deterministic, or can they be probabilistic, like maybe alternative? Because otherwise, it's only deterministic ones that are not relevant for kind of strategizing based on the say given by model.
Yep. No, so, okay, that's good. So, so there's a bunch of different ways, levels of modeling that you could do for an object that you're about to manipulate or the objects in the environment. Certainly you could have a distribution over beliefs of a particular geometry of an object, whether an object is there or not there, and you could have the same possibility for the environment, right? So, you know, I'm going to talk about octomap here, and that has some notion of probability baked into that. Okay, as a representation, but I would say a limited one, right? It's sort of just an occupancy probability. But I do think richer representations do include probability thinking. Mm-hmm. Okay, so there are many different representations. I mean, these days people are building incredible models of the environment with neural radiance fields or Gaussian splatting or whatever. But it's not immediately obvious whether those are the best representations, let's say, for collision-free motion planning. Okay, there's an oldie but goodie. It's not even that old, but it's, you know, things change fast, which is this octomaps idea. And I want to make sure you've sort of seen that representation. It's powerful, and it has a couple of the notions of scale that I want to make sure that I hammer home today. Okay, so I'll come over here. Okay, so building up, the first step is just thinking about a voxel grid. Okay, so imagine you've discretized your world into, let's say, I mean, for navigation, they tend to be big voxels, but for manipulation, if we want to reach into a narrow shelf, they might need to be smaller voxels, okay? So let's just discretize the entire 3D space. Into, I'll say 1 centimeter cubes. That's a little extreme, but I'll make the point, okay? All right, so you could imagine just a 3D representation that's sort of built up on understanding in a 3D, you know, basically every part of space that I've navigated, I want to put a 3D cube. We already used voxels a little bit to do downsampling of point clouds. Do you remember? Right? So if I've got point clouds coming in, and I have dense point clouds that may not line up from multiple frames, okay, I could summarize them somewhat efficiently by just saying, is there a point cloud? Is there an obstacle, true or false, in each 1 centimeter cube? That provides a natural discretization of the 3D space. The problem is, thinking about, you know, 1 centimeter times, you know, whatever, let's say I'm going to live in a home that's, I don't know, 100 meters, that's a big home. You know, some big, I was trying to use numbers, you know, simple numbers here, but some big home, okay, that's a lot of 1 centimeter cubes. Right? So we need efficient data structures to work with that. KD trees are a natural structure that you might have heard about before. But octomaps are based on oct trees. Okay, so if you want to find your way through the tree to a point at a certain location, you can start with a very extremely coarse discretization of the space. Let's say it's 2 bins in each direction, okay, at the top level. And then I decide, am I to the left or to the right of this, and I move in all 3 axes, which gives you 8 possible directions, okay? And then I refine myself into this smaller quadrant, orthant, and then and I keep refining down. And this gives me a multi-level representation that allows me to efficiently query and access a potentially dense voxel grid. Okay, and it's sort of particularly good in 3D space. KD trees are a more natural selection when you get to higher dimensional spaces, but for 3D, you can just split on the middle axis, and that scales because it's only 8 different choices. Yeah?
Yeah, plus like when we compare octrees over KD trees, or octrees split right now.
Yep, octrees split right in half in all of the directions simultaneously, whereas a KD tree splits one axis at a time. It's more natural in high dimensions. I think octrees are just super optimized for 3D. Okay. All right, so there's a couple things that are extremely good about that. So first of all, people, I think, underestimate. I underestimated when I first learned about this. We talked about it a little bit in the point cloud world, but how accurate of a model you can get, even if you're only using relatively coarse voxels. Okay. Once you do a marching cubes algorithm to sort of smooth out and try to find a contour, you get surprisingly accurate. This is a high fidelity geometry representation. It's capable of really representing complicated things. Okay, but it also supports efficient collision geometry queries. So for instance, if you want to say, like one of the really fast ones is trying to ask whether a sphere collide with a voxel. Let's say occupied voxel. That tends to be an efficient query. Finding the closest, it can be a little bit ungainly, but it can be done. And the other one that's sort of nice in this is doing ray casting queries. Okay, so if you want to update with your raw sensor data, and you have a point cloud coming in from your camera, and you get returns that are a certain distance, remember the point we made during ICP is that also tells you that all of the boxes between you and the camera are also not occupied. Okay, so octomap is an application of octrees which consumes raw sensor data, efficiently updates the probability. So there's basically a probability of anything being occupied based on the local sensor returns, and builds up these beautiful maps, okay, which can be high fidelity if you want to look at a tree at a centimeter kind of scale, but it also can be multi-resolution. If you want to do queries against things that are at a coarser resolution, then you can just stop earlier in your descent of the tree. And the reason I wanted to emphasize that, just for a second, is that this is one of the things that becomes extremely important when you try to scale, right? So once you get into really large environments, I might want to be thinking about the objects that I'm manipulating at 1 centimeter scale, but I don't want to be thinking about the door in the back of the room at 1 centimeter scale, right? There must be some sort of more flexible representation of the sort of precision that I'm thinking about. Sorry.
Yeah, I was going to ask how robust is octomap to data
Yeah. No, I think these were built for relatively high frequency sensors, I think why does high frequency strike you as a possible challenge? Oh, okay, good. All right, so if you're like an autonomous car and you're driving 70 miles an hour, maybe this isn't your tool. Sorry, I was thinking like slow robots moving through homes, and I think it's fine for that. It's true that you get a lot of new challenges once you get to like speeds that are similar to the sort of time of flight of your sensor. You have to think about distortion and all kinds of other effects that happen from that. Yes, so I'm not saying this couldn't work, but I think you'd have to unwarp a lot of distortion effects. You have to think about sort of scanning rates and other things like that when you start moving fast compared to your laser. But I think in home applications, the laser is way faster than your robot. Yeah, good question. Yeah.
If, for example, you're trying to you're in a grocery store, you're trying to detect a specific raw material, how might you use something like this to do something like that?
So great question. So this is, in some sense, what you do for all the things you don't want to manipulate, right? This is an excellent choice for sort of summarizing the collision geometry, but you're going to need to segment out something, anything of interest you want to segment out and do something different, probably. Yeah. This is like static known geometry. Yeah, good. Multi-resolution. Yeah. This is they're trying to show that it was occupied before and now it's not. But in fact, they're updating a count, and they have a Bayesian interpretation of a counting algorithm that basically will somehow say that the probability of this has gone down. Yeah. And this is the picture here is supposed to be that this laser was scanning up, so it saw this first here, and then it saw that it was here, and it's removing sort of the probability in that direction. I guess that is a little bit weird. It gives the impression that that half is filled and that half's not filled. I think the bucket is half full. Okay. So again, this is sort of, I think, mobile robots use this, even fixed-base robots, if you have complicated things in the environment that you don't want to interact with and you just have to reach around, they will use these even today, okay? And it's a nice representation because it starts to address the scale issues. People build octomaps of big environments, okay? And it actually impacts the way people build. So I've talked a little bit about the collision geometry being different than the visual geometry. And if you wonder why there's an EWA spheres collision, it's because of this. Because if you have voxel representations of your environment, we have super fast sphere collision checks. And if you want to do sample-based motion planning, then it's really convenient to have your robot approximated with spheres. And if you want to be more careful, then you build like spheres dense collision URDF. So you'll see a lot of robot models out here that actually have this kind of approximation. We have multiple different representations. We have like primitives that use boxes and other things, and as well as the spheres, and they're good for different motion planning queries. Okay, but when you have a voxel, the sphere is your friend. Cool. Okay, so that was like just a quick discussion about what is different about for perception. What's different about kinematics and motion planning? Okay. The number one thing I really want to say, and you're going to see on the problem set, is that the kinematics of the space, this is like a really good joint, especially if it's not limited to add in order to improve your reachability, your reachable workspace. If you're trying to sort of reach into a cupboard or something like this, then the ability to just sort of step to the side and reach is extremely good. Okay, but it does present a couple different challenges. So let's just talk a little bit about how the heck do you do the base? Okay, and I'll tell you my sad story at some point. Okay, so what's the simplest way? How do we think about planning for the base? So given what we've done, this is not the simplest way to build a mobile manipulator at home, but given the tools we've developed in class, what's the sort of simplest mobile manipulator? Okay, let's take our EWA, our WSG, okay, and I'm just going to add a few joints on the bottom. I'm just going to pretend that EWA has an actuator that's arbitrarily long in the x-axis, arbitrarily long in the y-axis. If I'm being friendly, maybe I'll even let it go up and down in z, because the best mobile manipulators do tend to have a z-axis. They can make a huge difference in sort of reaching into things. Okay, so plus just a prismatic base. Okay, and I mean that extremely literally. So here's the original EWA URDF. Is that big enough? Okay. It just is zoomed in to one piece, right? So originally the EWA actually had a link named base, okay? And then it has a simple fixed joint that takes link 0, which is that shoulder link-like thing, okay, and just welds it to link base. That's just what the shipped EWA model looks like. And what I'm advocating is extremely simple, right? We're just going to add a couple fake links. They don't have any geometry. They don't have any mass. That's okay. You don't want to have a link with no mass at the end of your kinematic chain, because then the dynamics would be undefined. But if it's at the root, that's fine. That's all good. You don't need any inertia or mass or anything here. Trivial, empty, fake links, okay? And I'm just going to put prismatic links between the base and this base x, prismatic between base x, base y. This one's in the x-axis, this one's in the y-axis, this one's in the z-axis. Okay? And then I put limits on here because I can't go below the ground and I can't go super high. Even that's pretty generous, okay? But, right? So this gives us a little mobile manipulator. Now, if I give you that mobile manipulator, and I ask you what changes about planning or kinematics, I think the answer you would immediately gravitate to is nothing, right? That's like just a couple of other links. No big deal, right? I've got a slightly different kinematic tree, but all of my kinematics queries still work. All of my inverse kinematics math still works, right? Nothing's really different. However, I feel that people, when they think about mobile bases, feel like it's a completely different thing, right? So I want to try to close the gap between thinking about a mobile base and thinking about it like this, as just a slightly more complicated robot with a couple extra links. Yeah? Did I see a hand over there? Good. Okay. All right, so how does it change the kinematics? Or even inverse kinematics? It really doesn't. Not the way we've been talking about it. I mean, if you were heavily using the sixed-off arm analytic solution, that one's not going to work for you anymore because you've got that more complicated linkage. But all the inverse kinematics tools really don't need to change that we've been using. Okay. Motion planning. This one, I might think a little bit about the scale having gone up a little bit. So a probabilistic roadmap in 7 dimensions is pretty darn good. In 10 dimensions, you're going to work a little bit harder to build a complete roadmap. You get too much farther than that, it might break the stack, but 10 sort of fits. 10's kind of okay. That's roughly what we would say we could do. I said +3 DOF, but okay. Trajectory optimization scales very nicely in dimension. I don't worry about it at all. The reason for that is because it's local, right? It's just thinking about a trajectory, and the trajectory could be in 100 dimensions. That wouldn't really screw up the local trajectory. Anything that's trying to cover space, that's going to suffer in terms of dimensionality. Okay, so nothing really changes if you use that prismatic base idea. It gets more interesting if you start having to use wheels. Okay? Okay, so there's kind of two important classes of wheeled robots. How many people did FIRST robotics? Yeah? I love that. I love that. That's completely changed, like, you guys. That's awesome. Right, so how many use this design? Right? Or versus this design? So right, these are the Omni wheels, right? This is one way to make a robot that can drive in any direction. And turn in any, the orientation's easy. I guess there's only one orientation on the plane, okay? But you can drive in any direction. as opposed to a non-holonomic robot, like a car, cannot instantaneously move sideways. Okay? This one can drive sideways, it can drive diagonal, it could drive whatever, right? And they're both of these concepts are based on clever wheels, right? These are the Omni wheels, these are the Swiss or Mecanum wheels, right? And if you have that kind of a platform, then there's some math you probably did in your first robotics competitions, in order to map the velocity of the wheel to the velocity of the vehicle, right? But then you can just plan as if you're a prismatic base, and you have to revert that mapping in order to send commands to your motors, but that just works. Okay, so really planning with this kind of a base is as simple as planning with the EWA on a floating thing. Okay, you might have slightly complicated velocity limits or something like this because of the way that mapping worked, but the first order, that abstraction holds. Okay. I actually, I showed this once before class the other day, but I'm going to show it again since it's my favorite thing. And anybody who's a first robotics person will like this, I think. So well, let me do this. So I think it's crazy, by the way, that first robotics doesn't use simulation. Right? They should all use simulation. But I know why, right? I think the problem is, you build your own robot, maybe you use SolidWorks. The advanced teams use SolidWorks, but a lot of people just hack and slash, right? Which is good. And the step of going from that into a simulator, that's the hard part. Like, someone can just build the environment once for everybody. But getting your robot into the simulation, especially if you're doing rapid design iterations, I think that's the bottleneck. And I think computer vision is good enough. We should be able to solve that now. So maybe there's not a too distant future where people can use, maybe they won't like simulation, but they should be able to use it. Yeah? This is not, no. So this is simulating the physics, okay? So there is just ellipsoidal collision geometry on the wheels, okay? And it's just friction. It's the standard Coulomb friction model. Okay, and I can drive this around and, drive over. Oh, there's a bump there, a pole there. It has. Isn't that cool? My daughter did first robotics, so I was trying to help her with this. She made this, and she spent a long time making sure that nobody could ever get over. But it's so tempting to try. Okay, so I think that's, I think it's super cool that Drake's physics engine can just do that. I actually thought we would have to use simplified models in order to simulate it effectively, but that's just all the closest we've come to tire mechanics. Okay, so what gets harder is if you have a non-holonomic base. Okay, so if you're more of a differential drive robot, then you do have some extra work to do. If you use standard tires, let's say pneumatic tires or something like this that don't have the ability to roll sideways, that's when you have a new constraint, right? This is not a theorem. There are ways that people can do it, but most of the time this implies a non-holonomic base, which means you can't move in arbitrary directions instantaneously. You'll see it. Now, the reason this is not quite a one-to-one mapping, I've seen, there are ways to, for instance, in fact, the TRI mobile manipulator has pneumatic wheels, but the wheels are actuated, so you can have wheels that can turn in place themselves, just with scraping along, and then you can almost instantaneously move in any direction. Then the approximation to a holonomic base is pretty good. But most of the time, you say a wheel, you cannot slide instantly to the side if you have a regular wheel. Therefore, you have a new constraint. There's a direction that I can't move instantaneously. It's if my wheel is pointed this way, then I cannot move this way. Yeah, instantaneously. Okay, so there's a couple different kinematic vehicle models that people use, right? So a standard differential drive. I apologize for my artistry. That looks more like a candy than a. Okay, but I've got some velocity command for wheel 1 and velocity command for wheel 2, and I'll have a total velocity for this thing, which maybe has components x dot, y dot, and then also a theta dot. Okay. And the standard model, the simplest model of this, the differential drive model, Dubin's model, Reed's-Shep model, they're all very similar. These are almost, I mean, they differ slightly by what you assume about the velocity constraints and things like that, and actuation constraints. Okay, but roughly they're based on models that look like this. Maybe let me just go ahead and write this as, so we use the notation of U for our input, U1, U2, U1, and U2. Okay? So if I have two control inputs, one of them is roughly my forward velocity. U2 is my turning rate. And I can map that down to the velocities of the wheels. And some of these models put the constraints on the wheel velocity. Some of them put it on the total forward velocity and turning rate. Okay, but they're all roughly going through this set of equations. All right, so now I have a slightly harder motion planning problem, right? In fact, this can be, I mean, if you've ever parallel parked, you know that this is, you know, that solutions can be interesting or complicated once you have that kind of a model. I mean, the differential drive robot, if it has small collision geometry, can do things you can't do with your car. You could just, if I wanted to go there, I could go like this, right? And you probably won't do that with your Prius or whatever, but that might not be optimal. That might not be the shortest path. It depends on your cost function and the like, okay? So there's a harder problem. You know, you can get solutions that start like this. You have a goal of being down here, and they'll do more like parallel parking kind of things to get there, right? That could be a shortest path. All right, so, and in particular, you just can't take the straight line path. You would at least have to turn. So this does change your motion planning, you know, somewhat significantly. So what should we know about that? Well, so first of all, I guess IK, importantly, there's no change in the inverse kinematics problem. Now, why do I say importantly? It's just a subtle point, but all configurations are still possible, right? This model is constrained in the velocities it can take, but it is not constrained in the positions that it could achieve, right? Unless there's collisions or other things that block it, okay? So from an inverse kinematics perspective, saying, can I be in a configuration with my base to achieve something? All configurations are still possible. Okay, for kinematic trajectory optimization and methods based on that kind of idea, then effectively, you're still going to search over continuous curves, but now there's a constraint. There's a derivative constraint on the continuous curves, okay? For the differential drive Dubin's kind of model, I think it's just that you can't move sideways, so it works out to be okay. So of all the curves that I'm going to search over, they must satisfy this equality constraint at every point. Now we can add those directly into the kinematic trajectory optimization library is rich enough to just take that as a derivative constraint. It tends to be enforced at points. You're going to be approximate. You might violate the constraint approximately in between, depending on how you've parameterized your curve. Okay, but likely you would do that. And otherwise, you would just solve the same kinematic trajectory optimization problem. You might be, you're asking for a lot more from your solver, right? It's going to have to potentially find clever solutions like this in its search over trajectories, but the machinery should work, okay? Which is pretty elegant, right? That's one of the things I really like about trajectory optimization is that you can just naturally describe the constraints on the curves. Okay? For sample-based planning, it's not quite as clear how you would consume that derivative constraint immediately. Does anybody know how people do sampling-based planning with this kind of a model? Yeah. Okay, so that's a good proposal. He says maybe you can do kinematic trajectory optimization between the points. Basically, pick a point at random and then just do kinematic trajectory optimization to get between those points. Oh, sorry, you were first. Okay, so the proposal was pick points, and if they don't satisfy the constraint, then throw it away. So the problem is that this is a measure zero sort of, this is a manifold of solutions. So you have to be pretty lucky to pick exactly where the constraint was satisfied. And you have to say something about the way it's interpolated. Yeah? But I like the idea, yeah? Okay, I think, so using splines or some sort of cleverly chosen curves, yeah? This picture kind of gives you that right? So you could sort of, you could sample over a subset of the degrees of freedom and then evaluate the one that you know based on the constraint. That's kind of the idea? Yeah? No, I like that. I like that all. In fact, I think the answer that has emerged in the literature is somehow in the convex hull of a lot of those ideas, right? And it turns out, so one proposal was to do the trajectory optimization. It turns out that, so the reason people don't do that in general is because if you're going to build an RRT with 10,000 points, doing a trajectory optimization every time you extend, that's bad news. That's going to be really slow, okay? There's cases where you might want to do that, but oftentimes that's not the favored opinion just because it's slow. It happens that for this particular model, which is particularly simple and particularly important, so a lot of smart people have spent a lot of time thinking about it, we actually can basically solve the unconstrained, and since there's no obstacles, kinematic trajectory optimization problem in closed form. Not quite, I mean, there's a numerical recipe that takes, that kicks out a solution very quickly. Okay? So for no obstacles, basically the diff drive on flat, let's say, open terrain. We have, let's say, exact solutions. Exact, fast solutions. It was kind of like a series of papers over many years where people finally said, like, okay, well, this version of this model, we found the closed form, or the exact solution. Okay, and then it took a couple more years to extend it to the case that was sort of the one that people wanted with the saturations, on the places, at the places people wanted. But we now have, exact fast solutions for the unconstrained case. But we don't want to only work on mobile robots, on the open, flat terrain, okay? So what has happened and come into favor is that you can combine that with sample-based motion planning. So pick a point at random, right? So I've got some tree. I pick a point at random. And now if this is my Q closest, and this is my Q random, I'll use the sampling base, or the exact solution to try to steer, they call them steering functions, to steer and solve this 2-point boundary value problem to get to the next random point. If that solution ever ran into an obstacle, then I'll just reject it. I'll just reject that point, okay? And with some arguments, you can still argue that this can give you a complete planar, because you'll eventually pick a point close enough that the trivial curve will satisfy for sort of unconstrained problems. Sorry, he was first, yeah.
Let's say I would use that technique for the Gantt tree, right? So could I reverse anything that because what I'm wondering about is that, like, if I have, let's say, 3 edges, one of them will be so big that I cannot take the turn.
Okay, this is great. So first, you said the word, let's extend this to the tree, which we're about to do. So, and let's distinguish that from graph, the road, but in the tree case, you start from the initial state, and you will only ever expand branches of your tree along feasible trajectories by this recipe from one starting point. Okay, so as soon as you get to the multi-starting point, then you have to be more careful about connecting and making sure that you only connect points that would be admissible. Yeah, but in the tree case, it's comes for free. Good point. Yeah.
But in the RRC case, that point that we're focused to are, let's say, the point to which we have a path.
Great. Okay, so the other step there was that we had to find our closest point. And for instance, these two states, they could be right next to each other in terms of my Euclidean distance metric, but they're actually very far, right? It might be that there's another state here that's like, I don't know, farther away by Euclidean distance than this, but it's actually, you can get there much easier than getting to the one right next to you. Okay, so how do people use that? It turns out that these exact solutions are for the minimum time problem. Okay, so the cost that you also have a sense of the cost. If you compute the minimum time from here to here, it not only says that this is how you get here, but this is the time it would take to get here. So you actually, when you sample possible points, you can evaluate their distance and choose the closest point based on the minimum time. So so I think you're exactly right to say you need a good distance metric for this to work, and this solution also gives you a good distance metric. It does help in probability 1, right, as time goes to infinity, right? So the story is, if I have I should use my multicolored chalk. If I had a red obstacle, and I have a start down here, it looks like a TIE fighter. That's what it looks like. And a goal up here, okay? Then at some point, if I draw enough random samples, I'll eventually pick a sample over here, and I'll steer myself here. I'll eventually pick a sample over here. I'll steer myself here, right? It's not, the sampling-based thing leaves room for optimality, but will eventually find its way around the goal, around the obstacles. Right? And it ends up with things that look like these. Your trees now have the canonical curves of the of the Dubin's car that are operating at the sort of steering limits. It tends to be a lot of points you try to connect will be right on the edge of the minimum time will drive solutions to the maximum velocity and maximum turning radius, almost always. Okay. Good. So any questions about the sort of holonomic versus non-holonomic base? We have good tools for motion planning to address them in most cases, but I do think the non-holonomic base makes the motion planning problems significantly harder, right? You have to do a lot more work. Yes? Yes, that's true in always with RRT kind of things. You tend to want to smooth it afterwards. And so I think I talked about some of the sort of smoothing where you connect points. That isn't as common in this setting, but you could do trajectory optimization, for instance, given that as an initial guess and try to find a good solution. You probably don't actually want to be driving at the limits. Minimum time is a problem that has a nice solution, but might not be the one you want for your mobile robot, right? So oftentimes there's smoothing afterwards, yes. Yes?
So there is a Voxel plot in there. Have you calculated that based on time?
Yes, that would, I think the standard objective is minimum time for all those curves. Yeah. That's right. Mm-hmm. So even when we're doing the kinematic motion planning with the non-holonomic base, I still want you to think about this actually, even though this drawing is suggested only in the mobile base coordinates. You could still extend the tree in the joint configuration space, which is the mobile base plus the joint angles. The interpolation of the mobile base coordinates has to follow these clever curves. The configuration, the joint coordinates could be straight lines, but you can still grow this and solve the problem jointly, right? You don't have to solve the planning problem for the base first and then the planning problem for the arm second, right? In fact, you probably don't want to if you want to figure out the best way to sort of reach into a shelf. The kinematic constraints of what your arm can do may completely determine where's the right place to drive your base to, right? Okay, so there is a subtle thing that comes up in the motion planning in trajectory optimization, sample-based, you name it. But one of the things that happens when you're trying to do, let's say, optimization for these, is once you have a mobile base, you have the ability to have a continuous revolute joint, right? So the problem is, here's what could happen, right? Is it could be that you're in this configuration now, and the best place you want to be is here. And you might accidentally choose to take the long way around, right? And you really need to do a little bit of differential geometry sort of thinking to avoid that and parameterize the space correctly so that the shortest path is actually not necessarily the one that stays between 0 and 2 pi or negative pi and pi. Okay? Yeah? I mean, that is roughly the fundamental question is what's the right way to do planning on the toroidal space? Yeah? Yeah? And this is something that Tommy's done some work on. So this is PR2. You'll see this set up on your problem set. Okay? So this is what can happen if you do trajectory optimization out of the box and ask the PR2 to reach in the shelf. And that happens. I mean, and you have to do a little bit of work to sort of avoid those kind of solutions. And if you read Tommy's paper, where's the, oh, Tommy, I can't get out. I did the full screen thing. Now I can't get to the next page. Ah. Okay. Here's the beautiful solution after Tommy's paper, okay? Which is doing graph of convex sets, but you have to choose that the convex sets never cross more than sort of the pi in order to have sets that sort of always wrap around and always take you in the right direction. And he's got a beautiful differential geometry general view of that kicked out a pretty simple algorithm in the end that works very well. Okay, here's my sad story. You ready? So remember the DARPA Robotics Challenge, okay? So let's just watch the robot do its thing real quick, and let me call out this task here where we had to pick up a drill, okay, and drill out the hole, and then we had to walk to the end, okay? So now let's look again. So look at the orientation of the robot at time 0, okay? Look at the orientation of the robot when he's operating at the drill, okay? It turns out we actually didn't, so we fell down during this task, and it was actually many weeks later when we were looking at the logs, we were like, oh my God, that was a pi over 2, it was a 2 pi error. We actually tried to go the wrong way around. So the series of events that led us to this was, first of all, so the robot's hand is way too big for the drill, but they made us turn on the drill, okay? So there's 2 drills there. We picked up the one drill, pressed the button. That was like one of the hardest things because his big old hand going, trying to press this little button, okay? And we start drilling. It took us just a little bit longer than it should have or something to get to the drill and start drilling, okay? We're halfway through the cut, so we had to cut a big hole out, right? We're halfway through the cut, the drill power times out. We knew there was a timeout on the drill. I don't know if we took longer or if that drill was like a little sensitive that day or whatever, but the drill stops drilling halfway through. We're stuck in the middle of the drywall, okay? This is like, you know, this was really a competition for $2 million, and we were like right near the end, and we were winning at the time, you know, whatever, but sour grapes. And so we're like, we're here, okay, the drill stops going. Like, what do? This is it was a sort of an advanced teleop interface, right? So we were commanding high-level actions, and the robot's autonomy was doing all the low-level actions. So we know that the robot's drill stopped. We know we're in trouble. But we have one last chance to win, okay? Yeah. Yeah, exactly. So first thing we did, we threw that drill down, okay? And we just go bam and started punching the wall. Okay, that didn't work. That might have also upset our robot a little bit, okay? And then there's a second drill, just in case, because they know this can be a problem. But the second drill is actually a different type, and our hand didn't work with that. So we try picking up the second drill, and we go back and we start doing the second drill. And then, yes, being, pi over 2 away from our initial condition, we tried to go from here to here, and we went like this. Yeah. So don't make that mistake. Yeah. It was a series of weird events that caused us to fall down. But we were doing well, you know, and I think the best team won. I'm not saying anything bad like that, but I just, it was funny that did screw up our good day. Okay. One more point to sort of make here. So what is different about simulation? And I want this to just remind you of what is possible for your projects, okay? So a lot of the simulations I've shown, and not really the ones that I've given examples of in the notes, are small scale, right? They're handfuls of objects on the tabletop. And there's another world of people that think about manipulation, mobile manipulation, that are thinking at a much larger level of sort of sim scale creation and asset curation, okay? So this is behavior 1K. That's one example. Let's see the little fetch robot, but it's in a really complicated environments. And the tasks, from a manipulations perspective, might be simple, although they've gotten some complicated tasks in there now too, okay? But it could be just like, get the milk out of the fridge. And the requirement there is this sort of situational understanding of the world, and then relatively basic motion planning, okay, and perception. But the scale of the challenge is bigger. And I think it's importantly bigger. I think it opens up the way you think about it. This is open source. So what I've been doing, for instance, okay, they've been getting more and more complicated behaviors. They're using Isaac simulation. So for the fluids, I'm not going to be able to help you, but for the other ones, we can mostly, this is partly what I was working on this weekend, was just importing other people's mobile manipulator assets into Drake if you want to use it that way. So we have importers for a lot of the formats. Sometimes when you import one that we don't use very often, it'll require more work on the parser. But I'm happy to do that work and try to close the gap. Yeah.
It's using like an e-wall with 3 extra rings in an acceptable way to make
Totally.
it.
Yeah. But that, so this is a beautiful way to make. This one is a beautiful way to make it. But you might want to have a kitchen environment. So hop on these sort of simulators, grab the assets from that. They already have the joints in the right place and stuff like this, and we can make sure that we'll parse it in and make it available. Yeah, I think for the robot, it's not. I think we have probably sufficient. Although I will try to make. We made progress on the spot simulation. Some of it's, I think the inertias are not going to be right yet, but the geometry is right and is available now. There's a couple different ones. That Habitat 3 is another one. 3D World is a local one. This is kind of that first scene is funny, but these are mobile manipulation challenges, if you will, okay, but at a room environment scale. And it does, I think it just, in the little ways I talked about today, but in the very subtle way that it just makes you think about the bigger version of the problem in, I think, a healthy way. So hopefully by the end of the week, we'll have more and more examples like this. I can parse the Google robot now and the Spot robot now and a handful of other ones. And if you want to work on this in the project, I'll try to make whichever one you want. Well, that's not true. I might influence you by the ones that are easy for me to make work. And we'll find some compromise that will get you a good mobile robot solution. Good. Okay. A little early, but that's good. We'll see you next time.